Okay, so we are still here in our studio, getting ready to work on the second half of this Introduction to Data chapter. So if you logged out, okay, and you logged back in, you may have went back to your home folder. If you did go back to your home folder, in other words, if you don't see the shared stuff here, you can click on the three dots. If you're in the share folder or the common folder and you do the little twiddle and click go, that takes you back to home. You see the little home here. But we want to be at the common folder to see the presentation. So /COM. Okay, we're going to choose my name. We're still in chapter 1. Okay, so we're moving on to the second part. We're going to view that in a web browser. Okay, so we left off with talking about how we could study variables to see if we saw any relationships between the two of them. Now, what we're going to look at today is sort of how we might study relationships specifically, or what might be particular ways we go about collecting data, and how we might structure this collection and what that might look like. Okay, so the first option for that we're going to look at are observational studies. Okay, so when we have these questions, like we said, that come up, once we look at a data set and we are wondering, is there a relationship between these two variables? There's going to be two common ways that we perform that investigation. We're going to do something called an observational study, or we'll look at the other in a second. Let's focus on the observational study first. This occurs when researchers collect data without interfering in any way. Okay, so that's what's called an observational study. We're pretty much just watching and collecting data in some way. They're observing values of explanatory and response variables. The data in NHANES comes from an observational study. Okay, we ask people, we're allowed to ask people, they can tell us. Okay, it's not that we have to just watch them and get the numbers ourselves. It can be reported, they can report that value to you. But most survey data is going to be an observational study. In an observational study, we can conclude a relationship between two variables, so we know that we can have an association, but we can't decide that one causes another. We don't have enough evidence to say that yet. For example, in our graph that we made last time, we looked and saw there was an association between height and the fastest you've ever driven a car. That was an observational study. So all we can say is that there appears to be an association or a relationship there. What we cannot say is how tall you were determines how fast you drive the car. Okay, that's not allowed from observational studies. One of the primary reasons that we can't do that is that our study can be impacted by some variables that we aren't necessarily looking at. Maybe we haven't even recorded. Maybe we don't even know about them. Sometimes those are called confounding variables, and they're variables that can have an influence on both the explanatory and response. So maybe it's not that the explanatory and response are driving each other, but something else is in common and driving both of them. Okay, if you look at your guided practice on page 1.11 on page 25, I'm sorry, it's number 1.11 on page 25 in the textbook, it gives us an example of where a confounding variable would crop up. Okay, suppose an observational study tracked sunscreen use and skin cancer in a large collection and found that the more sunscreen someone used, the more likely they were to have skin cancer. Okay, now does that mean that using sunscreen causes skin cancer? The conclusion sounds off. Okay, it should sound off because most of us, we think of using sunscreen as a way to avoid cancer. But it doesn't automatically mean that the collection of data was wrong or that the association isn't really true. The issue here is that there's likely a third confounding variable that we aren't considering. And most likely that's going to be, in this case, the amount of time spent in the sun. Okay, the more a person spends time in the sun, the more likely they are to use more sunscreen, and also the more likely they are to get skin cancer. So here's an example. Think about two variables that are associated with driving. Speed, okay, the average speed one drives on a highway, And tickets, the number of speeding tickets you get in the last 5 years. We say that speed causes tickets. If we say that, we believe that. If two people are alike in every other way, except that one drives faster than the other, okay, the only variable that's different between them is the speed. The one who drives faster has a greater chance of getting a ticket. If we truly believe that speed causes tickets, it alone has to be the great influencer. That might sound a little odd to you, okay? And it probably should, because we know there's more things that play into actually getting a ticket than just driving fast, okay? Another causal type of question: does smoking cause lung cancer? Okay. Explanatory, of course, is smoke. Does someone smoke? And the response variable is, do they have lung cancer? So both of these are categorical variables the way they're stated. The smoke is the explanatory, because if we're thinking about this relationship here, if we're trying to study this, we're asking, does the smoking cause the lung cancer? So independent and dependent in that relationship here. What we mean by the question: if two people are alike in every other way, except that one smokes and the other doesn't, is the one who smokes more likely to get lung cancer? That's what we mean when we're asking about causation. In a study of the relationship between explanatory and a response, we sometimes call confounding variables Z, and you might hear them stated as confounding if they're a third variable. They're associated with X but not caused by it, and also helps to cause Y. Okay? They're often present in observational studies because it's just not logical to believe we can ask a person every single question about every single part of their life to always be able to kind of flesh those out. An observational study finds that a brightly colored cars are more likely to receive tickets than cars of more drab colors. Does this mean the color of a car is a casual factor in whether or not its driver will get a ticket? Okay. The variable driving habits is a possible confounder here, and we don't know that. I mean, is it possible that a car, its color would catch the attention of a police officer? Well, sure, but if the person isn't speeding, then that car still probably isn't going to get a ticket. So we have driving habits as a confounder there. Why is it a confounder? It's not part of the two we're looking at. We're looking at variables here of color of the car and will they get a ticket. Okay, those are both categorical variables. We can't really say that there's a causal relationship there because we have driving habits, which plays some sort of a role in whether or not we end up with a ticket. People who drive fast are more likely than others to prefer sports cars. That might be one reason, which are often brightly colored, okay? And then their fast driving causes them to get lots of tickets. Okay, so when we're getting ready to do an observational study, we want to be able to get a good set of subjects. In order to draw any sort of conclusion about the data, it's important to be able to claim that our sample is representative of the population. In other words, we've got to be able to pick a sample that isn't going to be so different from the population that the data might appear differently just because of that. Okay, so here's a possibility. One way that we can get a good set of subjects. Should we let potential subjects choose whether or not to be in the sample? Should we let them volunteer? Now, let's think about if this is a good idea. First of all, a group of students conducting an opinion survey on food in the cafe, and they leave forms at the entrance for people to fill out. What do you think? Would this work? Okay, there's a problem here. The volunteers, even though if people fill this out, they'd fill out this survey, the responses we're going to get may not represent the entire population of students. Students who take time to fill out that survey are probably going to do so because they have a strong opinion, okay? They might be mad and they want to complain about it. Or they might have had an exceptionally good experience and they want to reward someone by complimenting them. They tend to be more on the extremes of opinions when we do volunteer surveys. If our goal is to get a real sample of opinion, we should avoid allowing participants to select themselves. Okay, generally volunteer is not a good idea. Another possibility, what about if the researchers choose? So if the individuals can't volunteer to be surveyed, what about if the people doing the study actually choose them? Should they get to decide who gets into the sample? Does that make sense? There's a problem here too. Researchers might wind up choosing people they know reasonably well for inclusion too frequently. Okay, people on your sports team, people in your sorority. Okay, that is a little bit of a convenience. They're closer to you. You're more likely to pick them. You have greater access to them. That might cause certain viewpoints to be over underrepresented. Not everybody in the entire school population is a sorority member. Okay, not everybody's on a sports team. So that population might differ from the whole group we're looking at. If researchers choose participants solely on the basis of whom they come in contact with, that's called convenience sampling, and it's not likely to result in good, reliable results from the data. So if you can't let the subjects pick and the researchers can't pick, who gets to decide and how do you handle this? The answer is random chance. Okay, you have to introduce some form of random sampling, okay, in order to have a valid, non-biased sample. Non-biased doesn't mean they have a strong opinion one way or the other necessarily. It just means that they are non-biased, would be they would represent the entire population. Not surprisingly, we just call this random sampling. We have a couple of types of that. We talk about simple random sampling. So basically, we're going to take a sample size n. So if you take that sample, you set that sample up so that every n subjects in the population has the same chance. So, if we were to throw everybody's name into a hat, shake them up, and choose randomly, simple random sampling. Okay. So SRS, simple random sampling is like having a box full of tickets, one for each member, randomly picking out one, setting it aside. Okay, until you've drawn in, or however many people you're going to put in the sample. So you draw them at random and you don't put them back in. So let's look at this example. Suppose you've got 4 rows. Each row has 6 people. You need a sample of 4. You pick one person at random from each row. Is that simple random sampling? No, it's not. Okay, because not every set of the size 4 has the same chance to be sampled. Okay, for an example, a set like this, 2 people from row 1, 1 from row 3, and 1 from row 4, that has no chance to be the sample selected. Every student might put numbers 1 through 24, a piece of paper in a box, and then randomly draw. Okay, we will assume that all random sampling is SRS unless we know otherwise. If it's not simple, that doesn't mean it's not random. Still a couple of other ways we can have random sampling. We can have what we call stratified and cluster. Stratified is where we break our population into 2 or more groups, and then we sample randomly within, simple random sampling from within. Suppose we want a sample size of 6 and we want to have equal gender representation. We might put male names in one box and female in the other, and then pick 3 from each. So we separated the population into groups and we picked an equal number from each so that we know we have equal representation. That's an example of stratified. Cluster is we divide population into several groups, and then we randomly choose groups and everybody in the group is selected. Okay, we could have the 4 rows of seats be our clusters and randomly select one row. So every person in that group would be picked. Okay, the difference here is stratified, we break into groups, but we only pick some out of each group. Okay, whereas with clusters, we break into groups and we pick everybody within one group or a particular number of groups. Right, so if we're not going to do an observational study, what's the other very common? Okay, the other type of investigation is a randomized experiment. Here we randomly assign subjects to different treatment groups, and within each group, each subject gets the same treatment, but different groups receive different treatments. Now, what does that mean? Here's an example. Let's say you wanted to know, does aspirin really prevent strokes? You assign a large group of individuals randomly to 2 groups. Group A is going to get aspirin regularly, while Group B doesn't. Okay, they would almost certainly take a placebo because we want to try to keep everything as similar as we can so that we know the only difference here is whether or not they get the aspirin. We assume random assignment would be more or less balancing traits of the individual groups so that the only significant difference between the 2 should be the treatment. Any difference in a long-term stroke rate. So if we monitored these people and we found out that we had more strokes in one group or the other, The only thing it would logically be attributed to would be the difference in the treatment or the difference in the aspirin. Okay, because we've made sure that that's the only difference between the two groups. Experiments can and do lead to a conclusion of causality. If we do an experiment, we can determine that one thing is definitely the cause of the other. Variables in experiments, researchers manipulate something and observe the effects of the manipulation on a response variable. Okay. Most commonly, manipulation consists of assigning the values of an explanatory to the subjects. So we just considered this experiment where we're talking about giving everybody a pill. One group gets a placebo, the other group gets aspirin. So that would be our explanatory variable. That's their treatment. Okay. The treatment must be the explanatory variable. If it's not, we're not going to be able to conclude if something caused something else. The response variable Y is the long-term stroke status. Did they have strokes or did they not? Okay. So your treatment, whatever treatment we're applying here, that's going to be our explanatory variable. Experimental units are subjects or individuals who participate. They don't have to be people. We can be testing out pieces of machinery. We can be possibly working on animals. It can be a vast number of things. The treatments are the different values of the explanatory variable, and subjects are broken into treatment groups. All members in the same group have the same treatment. So everybody who got an aspirin, everybody in their group would also get aspirin. If you were somebody who got the placebo, everybody in your group also got placebo. Okay, so what are the important things to remember about an experiment? Got to have control. There has to be one treatment group that doesn't get any treatment. We call that the standard. So that gives us kind of a blank slate to compare it to. Okay, if we see improvement, we don't want the improvement to just happen because everybody would have gotten better anyway. We want to know it's attributed to that specific treatment. We also want to make sure that we do all we can to make sure we get standard administration. Okay, so in other words, we want to administer the treatment at the same time of day, maybe. We want them to get the treatment in the same way, okay, maybe delivered by or at the same time of day, maybe with a meal or without a meal, those sorts of things. We want to try to keep it as consistent as we can. We also want to make sure that we have randomization of treatments to individuals and replication. If you do an experiment, you get particular results. If it's a good experiment, you should be, and the conclusion is solid, you should be able to repeat it again and again and again and get a repetitive result process. They may not be exactly the same results, but they're going to be similar in conclusion. Okay, so the experimental idea. Remember, observational studies can be bothered by confounding variables. Okay, so for an experiment, we want to try to eliminate that as much as possible. That's why we want to keep everything as close among these groups as we can, except for that treatment. We want it to be the only obvious difference. And in order to avoid bias, we always use chance to assign subjects to groups. Okay. If we have a completely randomized design, subjects are divided into available groups completely by chance. The treatment group has to have a particular size, and then every set of subject has the same chance to be in the treatment group. And then we also want to do something called blinding. We don't want the subject to know if they're getting the treatment or the placebo because that could affect their progression. And in that case, we call an experiment blind when the individual doesn't know what they're getting. But it also, sometimes they want to do what's called double blinding, where the researcher doesn't even know if they're getting a placebo or a treatment. Now, it doesn't mean no one knows. That information is recorded somewhere, but the researcher doesn't know. The person who's administering the treatment and the individual does not know. It keeps from any influence outside of the actual results being displayed. Sometimes we might want to block. We might want to break our subjects into groups or blocks. It's a lot like stratifying, okay? So when you want to block, you might have recorded the values of potentially confounding variables. If you know that gender might be part of that, it's advantageous when there's not a whole lot of subjects here. That might be an option to block if we are dealing with gender. If we have a lot of subjects, randomized design will work as well, even if there is a difference between groups, okay? But let's think about this. This is a good example for gender, especially. We'll see before long that men and women appear to have different mean levels of iron in the bloodstream. We have a data set that shows that in our studio. Gender is potentially confounding variable, okay, because it might be influencing um, that level of iron, and that's not something specifically that we're looking at here. We're not considering gender as part of the influence on that. So if we're trying to test an iron supplement, we would want to create both male and female blocks, because creating those blocks lets us compare men to men and women to women, so that we don't have to deal with that other variable in there possibly clouding our results.